Hello everybody. In this video we are going to continue the topic of the correlations of mass transfer coefficient, and we are going to see the correlations for flow through pipes. In the previous case we were discussing flow outside a cylinder, which is an outside flow, but here we are going to discuss the inner flow. You can call it like this. So for the flow inside the pipe, we are dealing with a case where we have a cylindrical pipe. This is the front view, this is the side view, and we have some mass transfer taking place between the inner side of the wall and the fluid, either from or to. So either the arrows are in this direction or in the other direction. So we have correlations for gas phase, we have correlations for liquid phase. Here in case of gas phase, this form is very close to the form of or the general form of the equation or the correlation of Sherwood number, Schmidt number, and Reynolds number. We have here constants multiplied by Reynolds power constant multiplied by Schmidt power constant, but here we have this it's Kd over d, which is Sherwood number, but it's multiplied by this logarithmic mean divided by the total pressure. So this term is part of the equation. So this PBLM is the logarithmic mean of partial pressure of B between the surface and the bulk. So this is partial pressure of B in the surface minus partial pressure of B infinity, which is in the bulk of the liquid or the gas phase, and this is the ln of the division or the ratio between these two. This is this correlation can be used for Reynolds number from 2000 to 35,000, and from Schmidt, and for Schmidt number from 0.6 to 2.5. For the liquid phase, it's almost the same correlation with the difference here that we don't have this P over P. So this is Sherwood number is this, and the power is different for Schmidt number. It's valid for the same values of Reynolds number, but for different values of Schmidt number. And this makes a lot of sense because Schmidt number is part of it is it consists of physical properties. So these physical properties for the liquid phases are going to be different from those for the gas phase. The diffusion coefficient for the liquid phase is smaller than the gas phase, and the density, viscosity are different as well. So that's why the range is different here. For laminar flow, there is a correlation that we can use for laminar flow where Reynolds number is less than 2000. So for all of these, we have large, relatively large Reynolds number. Here we have the low values of Reynolds number. And the condition, this condition must be satisfied that Reynolds multiplied by Schmidt multiplied by D over L must be larger than 10. In this case, we can use this correlation or this correlation. They are both the same thing. Either you can use Reynolds multiplied by Schmidt multiplied by D over L, or if you expand Reynolds Schmidt number, then you can reach this form. It's V infinity D square over L DAB. This is power 1 over 3, of course. So these are the correlations that we use for flow in pipes, inside pipes. For the next point, we'll discuss the weighted wall column, the mass transfer in a weighted wall column. But before we discuss the equation or see the equations, we need to understand what is this weighted wall column. So the weighted wall column is an experimental setup. It's a column, as you see. This is how it looks like here. It's a column that contains a reservoir at the top side. This is filled with a liquid, and this column has another reservoir at the bottom side of the column, and this column or the fluid that we have that's filling the reservoir on the top is or overflows. There is a weir here, so that it overflows and flows through the whole perimeter of the column. It flows in the inner side, so it doesn't fill the column. It just flows on the inner walls, and then we collect this liquid in the bottom part of the column. At the same time, we have a gas that flows in the other direction. So liquid is going from up to down, the gas is going from down to up, and through this flow process, you will have a transfer of species from the liquid phase to the gas phase, or the other way. And the main function, I'm discussing this to demonstrate the main function of this column. So the main function of this column is to measure the mass transfer coefficient. So this design is very strange. Why would I have a liquid that flows by the inner walls of a pipe? So this is made to make sure that we know the area of mass transfer. So in this case, the area of mass transfer is the inner area of the tube, which or the column, which is pi dl. So I know the total area of mass transfer, and from what I have here and what I have here in the bottom, I can tell the difference. So I can measure the difference in concentration in the beginning or in the end, or the amount if it's a pure component and it is evaporating. So I can tell what is the difference in the amount of species between the beginning and the ending of the mass transfer process. So I know the amount that's transferred, so I know the flux, and I know the driving force because I know the concentration here and I know the concentration in the gas phase. This is something I can control with this experiment. And I know the area, so I know so I know the rate, I'm sorry, not the flux. So I know the rate, I know the area, I know the driving force. So the only parameter that is not known is the mass transfer coefficient, which I can calculate from the rate equation. So this is the main function of the wetted wall column, to calculate the mass transfer coefficient. In this case, we can, the experiments showed that we can get the mass transfer coefficient in the wetted wall column using the same relation, that's KL over D or KZ over D. In this case, the characteristic length is the height of the column. And this is 0.433 multiplied by Schmidt power half multiplied by this term power 1/6 multiplied by Reynolds power 0.4. Here you have the density of the liquid. This is of course the acceleration due to gravity. This is the height of the column. This is the viscosity of the liquid phase. This is important to know that this is the mass transfer coefficient in the liquid phase. This is because we'll have here all these parameters are liquid phase parameters. This Reynolds number is liquid phase Reynolds number. So we do this for the liquid phase. For the gas phase, it's a gas flowing inside a pipe. So we can apply the equations that we just saw before to describe the mass transfer coefficient in the gas phase. But for the liquid phase, this is the equation that we use. And that's why all the physical properties here are gas phase physical properties. And even the diffusion coefficient is the diffusion coefficient of the species in the liquid phase, not the gas phase. This Reynolds number is calculated from this correlation. This is gamma. This is uppercase gamma. It's like the English letters. You have uppercase and lowercase letters. Here you have uppercase Greek letters and lowercase Greek letters. So this is uppercase gamma. So it's 4 gamma divided by mu L, and this is the mass flow rate of the liquid per unit parameter, which is the W, which is the flow rate, divided by the parameter, which is pi d. Okay, so it's W divided by pi d mu L, and this is 4. So this is how we calculate the Reynolds number, and we use it to substitute in this equation to get the Sherwood number. So this is all the correlations that we need to know, and it's getting clearer when we solve a problem. So this is going to be the topic of next video, inshallah. So I'll see you then.